So in this video, I want to talk about the notion of order of a differential equation. This is just going to be another way for us to concisely describe a differential equation that comes before us. We've already talked about one way of sort of classifying differential equations. In a previous video, we talked about the difference between an ordinary differential equation, an ODE, and a partial differential equation, a PDE. Order is just going to be yet another way that we can discuss and classify differential equations, kind of in the same way that we classify animals. Like that there are mammals and there are reptiles and there are amphibians. That's the work of doing what's called taxonomy of animals. We can do the work of taxonomizing differential equations. Okay, so this sequence of videos is really about doing that, giving different ways of describing differential equations to put them in different categories so that we can mentally sort of approach mentally kind of approach categories of differential equations all at once. Yeah, hopefully that made sense. Let me switch scenes here. Okay, so the order of a DE. Let's start with this. So let's just do this via example. One of the examples of a differential equation, which is really crucial for you to know and understand, is the exponential growth equation. That's y prime equals some constant k times y. This is called the exponential growth equation. It doesn't always represent growth, as we'll learn. If k is a negative value here, it's in fact exponential decay. But this is just a shorthand way of talking about this equation. Now, I asserted, why is it called the exponential growth equation? Well, because the solution to this ends up being y equals c times e to the kx. The exponential function, in other words, is involved in the solution to this differential equation. Now, have we solved this differential equation in the sense that have we figured out why the exponential this expression y equals c times e to the kx? Have I told you why this is the general solution? The answer is no. I won't merely asserted it, okay? But you can certainly verify for yourself that this is a solution, or this does represent an infinite family of solutions, simply by plugging in y equals ce to the kx into this equation and noting that it satisfies this here. And I won't do that here and now. You can look to previous videos to check that out. But here's what I want to say about this differential equation here. First of all, it's an ODE. So we're doing the work of taxonomizing. If we're going to place it in one of the two categories of an ODE or a PDE, we'll place it in the bucket of ODEs. Why ODE? Because there only is a regular kind of first semester calculus type derivative involved here. No partial derivatives in particular. So this is an ODE. It's also, by the way, a first order equation. And this is the thing that I'm wanting to focus on in this video. Why do we call it a first order equation? Well, that's because it involves only a first derivative. That's all. Okay? There's no second derivatives, no third derivatives involved in this equation. The highest order derivative involved in this equation is a first order derivative. Okay, another example. Let's look at Newton's second law, very important differential equation. F equals m, and you're probably screaming in your brain, A, right? Because you have heard the mantra many times in your life, F equals ma. And indeed, that is Newton's second law. But remember that acceleration itself is the second derivative of displacement. And that's how I want to display Newton's second law here and now. Let's write this as d squared s dt squared, where of course s of t is the displacement of some object at time t, perhaps relative to some origin where you set up a coordinate system at words. Okay, we have f equals m times d squared s dt squared. This is called Newton's second law, right? Very important. We're going to use it a lot in this class. And this is an ODE again, just like the previous equation. It's an ODE. But now we're talking about a second order equation. for, I hope, obvious reasons. It's second order because the highest derivative involved in this equation here is a second derivative. Okay? Finally, let's talk about a PDE, a partial differential equation, and use that as an example. We talked about the heat equation. I want to keep going with that because I love the heat equation. I think it's incredible. It's really cool. It's very useful in not even just physical context, but in other contexts as well. And we'll come to learn about the solutions to the heat equation once we get some Fourier theory out of the way. Okay? Out of the way. It's so interesting in and of itself. So let me remind you about the setup of the heat equation. If you have a bar, a long metal rod of some sort like this, okay, and you have a distribution of heat in this bar, all right, so that at position x along this bar and at time t, we call u of x of t the amount of heat in the bar at position x and time t. Heat at position x and time t. Okay? Then there is a partial differential equation which tells you about, and this is a fancy phrase, the dynamics of of the heat in the bar. So, you might imagine that, there's a certain distribution of heat. Maybe the left part is hotter and the right part is colder, or maybe the middle part is colder and the two ends are hot. Who knows? But the question that you want to ask yourself is, and we want to be able to answer is, how is this heat going to flow through the bar, which is a heat conducting material, as time moves forward? And there's a partial differential equation which governs that. It's called the heat equation, and here it is. It's that the partial derivative of u with respect to time is equal to some constant k times the second derivative of the heat with respect to space, with respect to position. This is called the heat equation. Okay. What is it? It's a PDE. It's not an ODE now. So just to contrast with the previous examples, this is a PDE for obvious reasons. It's got partial derivatives there, okay? It's got the fancy D instead of the boring D up here, okay? This should feel like third semester calculus, perhaps. Multivariable calculus. It's also a second order equation. Hopefully, again, for relatively obvious reasons. It involves a second derivative. See, second derivative. This despite the fact that there is a first derivative involved. It's a first derivative, it's got a first derivative with respect to time, but if we're going to talk about this equation overall, we're going to call it a second order differential equation. So this all leads us to make the following definition. The order of a DE is the highest order derivative appearing in the equation. And how do you detect the order? How do you calculate the order of a differential equation? You use your eyeballs, okay? You just look at it and you classify it that way, okay? All right. So, well, that's enough for this video. In the next video, we're going to talk about another sort of way of describing a very important class of differential equations that we are going to be obsessed with in this course, and that's linear differential equations. All right. See you in the next one.